So now let's talk about acceleration. Acceleration is the rate of change of velocity. Written as equation, A average, and again we'll come back to instantaneous later, is the change in velocity divided by the time it takes to change. So this rate of change means how much time did it take you to change. Change in velocity is change in velocity. Now this can be any change in velocity. So if you speed up, or if you slow down, or because velocity is a vector, if you change direction. In this unit and the next unit, we're going to be mostly dealing with speeding up and slowing down. We will include circular motion with the forces unit this year, and so that's when we'll get to, if you remember, centripetal acceleration. That's where this part of this will show up. So it's really important to think about the direction of your acceleration, because the direction of your acceleration tells you if you're speeding up and slowing down, but only in reference to your velocity. So if you are moving in the positive direction, whatever has been defined for the problem as the positive direction, but you're moving in the positive direction, and your acceleration is positive, then because you're accelerating in the same direction you're moving, you are going to see your object speed up. Now, if you're moving in the positive direction and your acceleration is negative, then you're going to see it slow down. And sometimes in problems, you'll be told, hey, this thing is slowing down at 3 meters per second squared. So you need to know to make the acceleration as negative when you put it in the problem. It will not necessarily be stated as a negative number. Negative acceleration does not mean slowing down. Negative acceleration means the acceleration is the direction opposite to whatever we defined as positive. If you're moving in the negative direction and you're accelerating in the negative direction, then you're speeding up because you're accelerating in the same direction as your velocity. And to finish the table, if you're moving in the negative direction but accelerating in the positive direction, then you're slowing down. So if they're the same, you speed up. If they're opposites, you slow down. And again, you're going to need to make those signs quite often. Occasionally they'll be given for you, but not always. When we get into free fall, the next section, that's especially when you need to think about that quite a bit. So we have 4 acceleration equations. I'm going to talk through 2 of them, and then I'm going to come up with 2 other ones. So this definition of acceleration, we can rewrite as final minus original in the time it takes. We're going to use, instead of time interval, like change in time on a clock, but this is the time interval. And if we do algebra, we cross multiply and we rearrange. This is the equation, the order in which this equation is usually written. So what this says is when you change velocity, depending on how much time you take, that's how much acceleration you get out of it. This is the same equation written a little differently that says whatever speed you start with, whatever velocity you start with, your rate of acceleration and the time you accelerate then give you how fast you're going afterwards. So if everything's positive here to make things easier, if you're already moving and you speed up for a certain amount of time, there's your final velocity. But the signs will fall out. So for instance, if this is positive, this is negative, you can imagine a situation where enough time would pass that eventually this whole term would be negative, which would mean you've turned around. You were going to the right, now you're going to the left. So how fast you're moving, important situation. The next equation, I'm going to go ahead and move the order up. So this is equation number 1. The next equation I'm going to talk about is how far do you travel? What is your displacement? This equation is not on the formula chart. So in AP Physics 1, I called it the 0th equation because we got it from graphing. So let me not write it over there. If you are traveling, how far you're going to travel depends on were you moving at the beginning? How fast did you speed up to? And how much time did you spend doing that? So if we go back to the very first equation, your average velocity times the time interval. So this is from, I should have written that first, v average equals delta x over delta t. So rearranging, displacement is however fast you travel, your average velocity times time. Well, if you're speeding up, you don't have a single velocity. What we called it last year was the midpoint velocity. Midpoint halfway between the starting and the ending. If and only if, and I'm going to write this, I'm going to use this new term, IFF, if and only if your acceleration is constant, then your average velocity is equal to the mean of your two velocities. Remember, mean in math is like the general English word average. Add all the things up, divide by the number on the list. So the mean of the initial and final velocity, so add the two up, divide by 2. If and only if your acceleration is constant, this average velocity is equal to the mean of the initial and final velocities. We'll get into non-constant acceleration a little bit later. So you can put these two equations together and I'm going to switch to the same t that I used in this equation. So your displacement is your average velocity over the time interval. How fast did you start? How fast did you end up? And then the time it takes to get there. This is the zero equation that is not on the AP formula chart. So you need to memorize this idea. Now, there are 2 more equations on the formula chart. There are really a total of 5 acceleration equations, but I do want to show you the math on how we get the other 2 that are most generally used. So if we start with this equation, number 0, delta x equals 1/2 v naught plus v times t, and then we substitute number 1. So sub number 1 for v. We are going to get delta x equals 1/2, open, I'm going to change it to brackets because it's going to be so long, v naught plus, instead of v, I write v naught plus at, all times t. Move this up. So I'm going to simplify in the parentheses first. So delta x equals 1/2 2 v naught plus at, all times t. And remember, hippity-hoppity distributive property. So I need to distribute the 1/2, and I need to distribute the t. So this 1/2 times 2 cancels out. We're left with v naught and then times t, plus 1/2, there's no coefficient, so that is the coefficient, at times t, so at squared. And you should recognize this. This is equation number 2 on the College Board formula chart. To get equation number 3, we are again go back to equation number 1, but solve for t. So making sure it's on the screen. If I cross multiply and then divide by this, t equals v minus v naught over a. I'm going to put this in for t, substitute into number 0. So delta x equals 1/2 v naught plus v times v minus v naught over a. And that looks really messy. So first thing I'm going to do is get rid of my denominator. So multiply both sides by 2 and a. So I get 2a delta x equals v naught plus v times v minus v naught. Now you should recognize this. If you FOIL this out, this is the difference between 2 squares. So 2a delta x equals v squared minus v naught squared. And then we rearrange, isolating v squared by adding v naught squared to the other side. v squared equals v naught squared plus 2a delta x. And so that is the third equation on the formula chart. So let me grab another pen. Number 1, number 0 that you just have to memorize, number 2, and number 3. And the last part was barely on the screen, so let me mark that up a little bit. So there is a fifth equation. We could do this whole thing again, because you'll notice every one of these equations includes the initial velocity. Something's missing from every one of them. This was one way we knew how to pick equations last year. Number 1 is missing displacement. Number 2 is missing the value of the acceleration. There is acceleration happening here, but it's missing the value of it. Number 0. Number 2 is missing the final velocity, and number 3 is missing time. So this is most useful if you don't know or care about the time. This is most useful if you don't know or care about the final velocity. So all of them include the initial velocity. There is a fifth equation that does not include the initial velocity, but it's very rarely used and you won't even see it in most physics textbooks, so we're going to skip it. So now we're going to do an example problem. So suppose a car is merging onto the freeway. The car is initially traveling at 10 meters per second, and the ramp is 200 meters long. The car accelerates at 2 meters per second squared. How long does it take to travel up the ramp? So we need to identify information. We know the car is initially traveling at 10 meters per second. The ramp is 200 meters long. The car accelerates at this rate. And our question is, how long does it take? So there are 5 total variables: a, v naught, v, x, and t, delta x, sorry. So acceleration, initial velocity, final velocity, displacement, and time interval. So we know the acceleration is 2 meters per second squared. We know the initial velocity. We don't know the final velocity. We do know the displacement, and we're asked to solve for time. So if you look back in your notes or you look on the formula chart, handy dandy formula chart, you either say, okay, I'm looking for time, so the first equation won't work because I don't know the final velocity. The 0 equation won't work because I don't know the final velocity. The third equation, or excuse me, the second equation will work. So if we work from delta x equals v naught t plus 1/2 at squared, I usually have encouraged you to rearrange this algebraically before you start. But there's a slight problem in this one. I'm going to plug in numbers and I'm going to drop my units while I plug in numbers because it gets kind of messy. So 200 equals 10 times t plus 1/2 times 2 times t squared. Now I can simplify this. 200 equals 10t plus 1/2 of 2 is 1 plus t squared. And then we have to stop. Because we have both a t and a t squared, the only way to solve this is with the quadratic formula. And you know the quadratic formula. If an equation is written in standard form, a squared plus bx plus c equals 0, then, and yes, I'm going to sing, x equals negative b plus or minus square root of b squared minus 4ac all over 2a. Now, this song is kind of fun to sing, but no one really likes to do the quadratic formula. So you have a couple of choices at this point. The first thing you can do is to use a graphing calculator and plug it into the math solver function. And I'm not going to show you how to do this, but if you have a TI, or excuse me, any graphing calculator, I can show you how to do it in class. The other option is to say, well, instead of going through the pain and suffering of using the quadratic formula, I'd rather do 2 physics equations and then get my answer. So I don't need to know V to solve this problem, but then I have to use the quadratic formula. What I could do, since I know A, V naught, and delta x, I could get the final velocity from equation number 3. V squared equals V naught squared plus 2A delta x. Let me slide this up some more. So V squared equals 10 squared plus 2 times 2 times 200. So this is 800 plus 100 is 900. And the square root of 900, oh, shame on me, I did put that in the calculator, is 30 meters per second. So this car, 10 squared plus 2 times 2 times 200. Oh, yes, yes, yes. Sorry, I'm remembering something from my notes. So this car has accelerated from 10 meters per second to 30 meters per second. As an aside, I want you to remember that 40 meters per second is approximately 100 miles per hour. So that a car speeds up to 30 meters per second means that's about 75 miles per hour. So that is a highway speed, but I picked nice pretty numbers for this. Well, now that I knew the final velocity, I can use the first equation or the zero equation to find the time. So I think I'm going to use number 1. V equals V naught plus AT. So 30 equals 10 plus 2 times t. So subtract to get 20, 2t. So this took 10 seconds. So there's my answer. If this was the test question, I would love to see all this written out. You could even write this. So I got to use the quadratic formula. Maybe you cross it off. You can switch to other stuff. But please notice how I wrote the original equation, then I substituted in and wrote my answer. I don't need to see all the little steps. Like this one really is not required for showing your work. I am assuming that y'all are very good at algebra. Let's go with that. Now, here's the one thing I will do. Back in this equation, since this is the one that did not require me to know the final velocity, I'm going to plug into this to check my work. So 200 question mark, does this equal 10 times the time of 10 plus 10 squared? So 10 times 10 is 100, plus 10 squared is 100. Yes. And because these two sides are equal, if I had used the quadratic formula, it turns out I would have gotten 10 seconds. That's really not so bad since I made up such pretty numbers. If they're not pretty numbers, it can be annoying. Now please, if they're not pretty numbers and you end up getting here 200 equals 199.97, those are the same. Don't make me scream. Okay, so that's a nice big acceleration problem, and that's what you'll be doing in class tomorrow.